Okay, next we're going to look at another extension of geometric algorithms to process slightly more complicated objects, and then we'll see an important application. And this is called interval search. So now, instead of points, our data is intervals. So this is, we'll start with one dimension as before, and right away I can see that it's a more complicated problem than we've been dealing with. So we want to support the following operations. We want to be able to insert an interval. So an interval is just a left endpoint, right endpoint of one-dimensional data, or points on the line. We want to be able to insert an interval, search for an interval, delete an interval, but the main thing is we want the interval intersection query. So given a query interval, we want to find all intervals in the data structure that overlap that interval, or find any interval. We'll start with that simpler problem. So how are we going to support that? So this is the API in Java code. We have intervals, so instead of one key we have two, which is the left and right endpoints of the interval for put and get, and then we have delete, and then we're going to have the intersects. And again, to simplify the code, we're going to make the non-degeneracy assumption that no two intervals have the same left endpoint. That's easy to fix, but we don't simplify the code. So now we'll look at a data structure called an interval search tree that helps to solve this problem. It's an extremely simple algorithm, but surprisingly complicated to understand, so we'll go slowly. So the first thing is, what we're going to do is use the left endpoint of each interval as the binary search tree key. So our nodes store intervals, but we only use the left endpoint as the key. So this is the binary search tree that's built from those 6 intervals in our example. 17, 19's at the root, so everybody with a left endpoint less than 17's to the left, and everybody with a left endpoint greater than 17's to the right, and so forth. So that's a binary search tree built from those intervals. So that's easy. Just build a binary search tree. Just use the left endpoint as the search key. But we're also, in each node of the tree, we're going to store not just the interval, but we're going to store the largest endpoint in the subtree rooted at that node. So at every node, we're going to store the maximum endpoint in the subtree rooted at that node. So at the root, the maximum endpoint, or the rightmost point covered by an interval, is 24. So we store 24 at the root, and of course the right subtree. In the left subtree, the max endpoint is at 18, so that's what we store for the associated data with the node to the left of the root, and so forth. We're going to have to, that's data that we're going to have to maintain when we do an insert, and it's data that we'll use when we're doing an interval intersection search. So let's take a look at a insertion into an interval search tree with a demo. All right, so the insertion algorithm is pretty simple. We do the BST insertion, it's just that we have to do that update of the maximum in each node on the search path. So to insert 1622 in this tree, well, we use the left endpoint as the search key. 16 is the left endpoint of our insert interval. We compare that with 17 and therefore go left. Now 16 is bigger than 5, so we go right. Now 16 is bigger than 15, so we go right. And that's null, so that's where we insert our new interval. So now we're going to go back up the tree, and for every node that we encounter, it could be that our right endpoint of our interval is bigger than what was there, so we have to check all the way up the path the maximum in each node on the path. So we have to check each node to see if 22 is bigger, and for the 3 nodes to the left, it is bigger than 18. For the node at the root, it's not, that stays to be 24. So it's just binary tree insertion, but then after the insertion on the way up, we go ahead and check if the maximum that we have is bigger than the maximum there and update it if necessary. So easy to code. All right, so now about how do we do a search. So the search is definitely more complicated and kind of mysterious, but let's look at the rules for search in an interval search tree. All right, so now we're going to look to see if we have an intersection. We want to find just any interval that intersects this query interval 23, 25. We're not going to try to find them all. We'll get back to that in a minute. Try to find any interval that intersects our query interval. So let's see what we have to do. So first thing is, if at the root we have an intersection, then we're done. We just return. In this case, 23, 25 does not intersect 17, 19. So we have to go down the tree somewhere. So left subtree is null, go right, okay. Otherwise, we have to check whether the max endpoint in the left subtree is less than the low point in our interval. And it's easy to see, well, if that's the case, then we're not going to find an intersection in the left. The maximum endpoint in the left is 22, and we're looking for 23. We're not going to find anything there, so we just want to go right. So in this case, we'll go right. 22 to 23, no intersection on the left, so we go right. And now we do find an intersection. 21, 24 does intersect with 23, 25 because 23 is in the middle there. So we find an intersection. Now, on the other hand, let's say that we're looking for 12, 14. No intersection. All the algorithm says is that if you didn't go right, go left. So let's go left in this case. So we weren't able to show that there was no intersection on the left, so we're going to go left. In this case, we compared 12, 14 to 5, 8. So now we apply the same rules. Does it intersect? No, it doesn't intersect. Should we go left? Well, no, the maximum endpoint in the left node is 8, so we can't have an intersection there, so we're going to go right. Compare 8 to 12 and go right. So now does 12, 14 intersect 15, 18? It does not. So there's no intersection. So now what do? Should we go left? No, the max endpoint on the left is 10, so we shouldn't go left. We're going to go right. Does 12, 14 intersect 16, 22? It does not. Now the left endpoint's null, and so we're just going to go right, and there's no intersection. So in both cases, we just went along one path in the tree to determine whether or not there was an interval intersection. Let's look at one more example, 21, 23. Let's see, 21 through 23 to 17, 19. They do not intersect. So now what are we going to do next? We're going to compare the left subtree, and it's not, 22 falls within our interval, it's not less than ours, so there might be an intersection there, so we better go to the left. So we do go to the left. Now we compare against 5, 8, and there's no intersection. So now we're going to go left or right. Well, we're going to go to the right because the max endpoint in the left subtree is 8, and our interval is 21, so no intersection on the left, so we're going to go right. Intersection 21, 23, 15, 18, they do not intersect, so now do we go left or right? Again, 10 is less than our left endpoint 21, so we better go to the right. And now 2123 does intersect 1622, so we return an intersection. Again, one path through the tree to determine an intersection. So from those rules, you can see that the amount of code required to implement this intersecting interval is extremely low. We just check for an intersection. If we find it, return. If left is null, we go right. Otherwise, if the max is less than low, we go right. Otherwise, we go left. It could hardly be simpler. A really amazingly simple and efficient algorithm. We should convince ourselves really that it always works, and so we'll spend just a moment on a short proof. So let's look at the cases that could happen. First thing is, if the search goes right, then there's no intersection in the left. And that's easy to convince ourselves of that just from what we did in the demo. Of course, if the left subtree is empty, there's no intersection there. But if the max endpoint in the left subtree is less than low, that means every interval in the left subtree has a max endpoint less than low, and so therefore it can't intersect. So if you go right, there's no intersection in the left. Any possible intersection would have to be in the right. And then the other point is that if you go left, then either there's an intersection there or there's no intersections at all. Let's suppose that there's no intersection, and that's equivalent to saying if there's no intersection in the left, then there's no intersection in the right. So let's look at if there's no intersection in the left. Since we went to the left, and then we've got low less than max. But for any interval in the right subtree, it's got to appear after low because since there's no intersections in the left subtree, high has got to be less than C because they're sorted by left endpoint. And then that means that C's got to be less than A if A is in the right, so then therefore there can't be any intersection in the right either. No intersection in the left means no intersections at all, so those two cases is enough to show that this algorithm finds an intersection if there is one. And the other thing we can do with this is just use a red-black BST to guarantee that we solve this in time proportional to log n. So insert, find, delete, and find any interval that intersects all take time guaranteed proportional to log n. And if we want to find all intervals, we just have to run the algorithm for each interval that's until we come up against no intersection. So it'll take time proportional to r log n if there's r intervals that intersect. The theoretical best that you could possibly do would be r plus log n, but in practice r log n is quite efficient. This is an easy and very efficient algorithm to solve this interval search problem. And as we'll see, this algorithm is applicable to an important application that we'll see in a minute.